Please join me in welcoming the third finalist team from Spanish Aviation Safety and Security Agency.
Good morning. I am Verónica Elvira. I am Deputy Director of Safety Analysis at AESA, the Spanish Aviation Safety and Security Agency. Today, we shall present to you the journey while developing our project, RIMAS, a breakthrough in aviation safety risk management with the aid of operation research and analytics. We are proud of being here today in this Edelman final in presence of this audience and with such excellent finalist companions. We have divided the presentation into 3 different parts. We shall start by arguing for the critical need of operation research and analytics in aviation safety. Then, we refer to the challenges that we have to deal with, in particular when developing the Spanish Aviation Safety Program. Then, we will outline our solution and will present the impact that RIMAS has had in making Spanish skies safer. After all, recall that we are in the safety sector. This is mainly about avoiding accidents. It is mainly about saving lives. And as someone once said, whoever saves one life, saves the world entire. Let's move then on to the relevance of operation research and analytics in aviation safety. They have helped us in transforming the risk management processes in our organization. Man has always dreamed of flying. We all know the history of Daedalus and Icarus from the Greek mythology. They wanted to escape from King Minos. Daedalus created gigantic wings using branches connecting them with wax. He explained Icarus how to fly, but told him to keep away from the sun, as the heat would destroy the wings. Daedalus and Icarus flew to the sky. The flight of Daedalus and Icarus was the first time that man managed to fight the laws of nature trying to fly. We all know also the flying invention of Leonardo da Vinci, the first motor flight by the Wright brothers, precursors of the ultra-sophisticated aviation of our days. Air transport is fundamental for the development of modern societies. It is a very complex system with growing volumes of traffic. On the screen, we can see how there are areas with huge traffic density, such as Europe or North America. On the other hand, air transport is affected by the need for airlines to reduce costs while improving safety. Can this be managed by intuition? It is therefore necessary that authorities guarantee air safety by using data and evidence to obtain insights and make better decisions. Indeed, all member countries of the International Civil Aviation Organization, ICAO, are mandated to develop a so-called state safety program, which expresses how national aviation safety resources are allocated to enhance safety in the country. In Spain, AESA coordinates the program as its associated action plan. This is a very important document elaborated annually as the involved stakeholders, airlines, airports, need to align their safety management system with the state safety program. AESA takes care of making Spanish skies safer. It handles a very complex system, which includes airlines, airports, air traffic management installation, aircraft, and people in numerous roles, including pilots, passengers, or maintenance staff. More than 2 million operations take place annually in Spain. Aviation is crucial for a country like ours, which heavily depends on tourism. Moreover, safety is essential for the healthy development of aviation. Imagine for a moment that we had a proliferation of events as the ones we saw, in which a plane might crash with numerous fatalities or result in its destruction. However, safety is also about more modest events rarely making to the news, like ground collisions, bird strikes, or hard landings. Maybe you experienced it last Saturday when you arrived to Austin. The entailing impacts like repairs, delays, or injuries, which on the whole aggregate to the difficult mission of the aviation safety manager. Luckily, we have made a long journey since the beginning of commercial aviation. And indeed, it is a truly safe transportation mean, as shown in this graph, in which accidents seem to be decreasing. However, we should be careful because some of them might be worse and fatalities might increase. In addition, this is not sufficient in a context in which traffic and competition are growing constantly. We cannot eliminate accidents and serious incidents. Failures and operational errors will occur in aviation, in spite of our best efforts to prevent them. No human activity or human-made system can be guaranteed to be absolutely free from hazards. But safety risks and operational errors must be controlled to a reasonable degree. It is interesting to note that despite the economic importance of the aviation sector and its technological sophistication, the risk management paradigms proposed by ICAO and other organizations such as the European Aviation Safety Agency are based mainly on risk matrices, which have been criticized in various academic publications. Thus, our organization wanted to go beyond such traditional aviation risk management standards and develop new quantitative methodologies. Given such a state of affairs and state of the art, several of the leading members of AESA, including myself, decided to undertake a master in decision engineering. It was crystal clear for us that the way forward to overcome such impasse was through operational research and analytics. Therefore, we decided to collaborate with the Spanish Royal Academy of Sciences to improve the standards as expressed by our director in this clip.
The old tools are much simpler. With RIMAS, we have the opportunity to work with advanced analytics and operational research techniques that bring us the opportunity to allocate and use in a more efficient way our resources.
The new approach to allocate resources and the challenges in this breakthrough transformation will be presented to you by David Rios from the Royal Academy.
So thanks, Veronica, and good morning, everybody. I feel extremely fortunate for having partnered with AESA in this project, which covers all complexities and subtleties that we present when referring to advanced OR analytics, including the presence of multiple sources of uncertainty, the presence of multiple objectives, the very high stakes involved, including lives or crashes of aircrafts, a highly dynamic environment, the need to intertwine strategic and operational decisions, or the need to deal with heterogeneous large dimension databases involved, like ECAIRS, for example, the European Occurrence Database, or the Aviation Safety Network Database, which covers accidents from the last 60 years. To give further ideas on the complexity of the problem, know that AESA needs to deal with 88 different types of occurrences, including hard landings, motor failures, bird strikes, or runway excursions, with different likelihoods of occurrence and impact. Each occurrence is classified in one of 5 relevance categories, from minor, significant, major, serious, and accidents, and affects one or more aircraft group according to its weight. In a nutshell, the problem the aviation safety risk management problem needs to deal with is described through simple inference diagrams in which we need to forecast the number of operations, the number of occurrences, which depends on the occurrence rate, the occurrences per type, which depends on the proportions per severity, which will have several outcomes like fatalities, as we shall see in a moment. These are aggregated through a loss function, and we then must decide the portfolio of resources that must be used, given the constraints of our organization, to reduce the likelihood and or the impact of such occurrences as much as possible. The problem gets more complicated as we need to consider multiple occurrence types of different nature. With the vision of continuously improving safety over Spanish skies, our operations research-based approach to aviation safety can be briefly sketched through activities over several phases, requiring models to forecast incidents and their outcomes, assessing such outcomes, and then using various model ingredients for purposes such as monitoring, safety assessment, screening, and resource allocation. In these phases, we use methods and tools for large-scale forecasting and analytics, multi-attribute decision-making, optimization, and simulation. However, before sketching some details, recall that, as Veronica said, all this is about safety. After long debates within its top management, AESA decided to focus on managing safety according to the main principle of minimizing fatalities, with other important objectives, such as minimizing crashed aircrafts and the country reputation loss, measured with a proxy attribute of accidents, a number of accidents in commercial flights. Other objectives included were considered less important but still relevant, and include minimizing injuries, repairs, and safety-induced cancellations and delays. Probably the most innovative phase of RIMAS, from a methodological point of view, has been our occurrence forecasting approach, used both for risk assessment and safety monitoring purposes. In particular, the number of operations and the occurrence rates are uncertain, and our models need to reflect this. Such rates may show a number of effects, like a stress effect associated with the increasing number of operations, or the presence of seasonality as shown in the figures. Another relevant effect is correlation. Besides, we should take advantage of all the prior information available at AESA. We therefore need a class of models versatile enough to cope with such features as follows. The upper block represents a dynamic linear model to forecast the number of operations. The bottom block is another dynamic linear model to learn the logarithm of the occurrence rate. And the intermediate block is a Poisson model, which depends on the number of operations and the rate. Dynamic linear models can take care of stress effects, seasonal effects, and trend effects, as well as occurrence correlations. And finally, the priors there reflected encapsulate prior knowledge at AESA. This methodology has been validated with AESA's historical databases and has allowed us to accurately catch up forecasts of the 88 types of occurrences. Just with this class of models, we may already introduce relevant uses in AESA practice through improved methods to monitor safety, which is an essential part of any safety program, as we reflect in the figure with an example of bird strikes, which is a typically seasonal phenomenon. Through the predictive intervals issued, we may detect anomalous observations to set up alarms when something is going wrong, going worse than predicted, and consequently try to identify causes and make decisions like non-scheduled inspections, contacts with airports, and so on. It could also be the case that something is going better than predicted, and we could study this to identify possible good practices. Forecasting outcomes demanded also a lot of innovation because of lack of available literature and the huge amount of cases to be considered, resulting in 1,760 models, little forecasting models, given the various occurrence types, severities, aircraft types, and outcomes. We had to answer questions like, given that a serious engine failure happens with an aircraft of type 3, how many severe injuries would you expect? We sketch here the generic model for fatalities, which involves forecasting the proportion of fatalities, the occupancy, and the maximum occupancy. As another example, we sketch there what we did for delays, for which we use a mixture model, which considers that there may be or may not be delays, and that such delay could have or not a network effect. In addition, for example, we had to assess such delays with an operational cost model of delay derived from Eurocontrol. All models were evaluated for their fit both individually and hierarchically with AESA and other databases. At this point, I would like to stress that the large forecasting effort involved had to be somehow factorized. Another major ingredient for our approach was to assess and aggregate multiple outcomes through multiple attribute loss function. For this, we aggregated the impacts with weights coming from cost models available from public data, mainly from Eurocontrol. Also, for example, the reputation loss required a specific elicitation based on the standard method of swing weights. This loss model allowed us to introduce the idea of equivalent safety cost. But we also had to account for the risk aversion of AESA. Based on the described forecasting and loss models, we were able to simulate from the system to assess its current effectiveness, as illustrated in the figure. And given the high equivalent costs, it seemed necessary to manage the associated risks. Such ingredients are also instrumental in developing simulation aviation safety risk maps, which portray, in this case, the 88 occurrences according to their predictive likelihood and impact. This will be essential, as I will say later on, for our screening approach. Moreover, the risk maps are used to build the risk matrices demanded so far by the international authorities, as Veronica mentioned before. And they are illustrated in these features, which are actual outputs from our RIMAS system. Such model ingredients are also essential for the major challenge in aviation safety risk management, which refers to optimizing aviation safety resource allocation. Our main model refers to how we allocate inspection resources in terms of time to various occurrences, defined as fractions of the available time. Once with the model for their impact, we may estimate the expected loss associated with a policy. And we would then look for a policy with minimum expected loss. We can include constraints referring, for example, to upper and lower bounds for resources, to various occurrences or groups of occurrences. And the corresponding optimization problem provides us with the proposed best allocation of inspection resources. What we do then is to simulate such policy to feel reassured about its relevance and robustness so as to build trust in the policy makers. With all these elements and models in place, we summarize now our approach based on analytics and operations research to establish the state safety program. First, we use the risk map, essentially use the risk map to screen occurrences. Note that in such map, as expressed there, the more we go to the northeast, the worse the impacts and the likelihood. And recall that we want to identify the worst occurrences over which we should concentrate our risk management efforts. For this reason, we determine first the occurrences in the anti-Pareto frontier, which are marked in red. We also include in this screening those occurrences which tend to occur more frequently or are more costly, defined by chosen cutting thresholds, as indicated in the figure. Moreover, we pay attention to those occurrences predicted to go worse over the year compared with the earlier one, for example, those marked in blue in this case. Finally, we detect what are called emergent or novel issues. We marked it in green, like those, for example, related recently with drones. This provides AESA with a list of occurrences which, for one or more reasons, deserve further attention for the agency. We then proceed with optimizing the resource allocation, as explained before. And finally, the suggested recommendations are checked by the agency experts and pass to the senior management, which makes the final decision. My colleague, Fran Bernal, who is head of aerodromes and air navigation risk analysis at AESA, will now present you the implementation and impact of RIMAS.
Thanks, David, and good morning to everybody. David has sketched you a breakthrough approach to aviation safety risk management, which makes full use of OR and analytics, as well as advanced computing, data engineering, visualization, and of course, lots of domain knowledge from aviation safety. The main objective of AESA, as reflected in the diagram on the left of this slide, is to optimize and improve safety. David Rios and his team of the Royal Academy of Sciences offered us an innovative and advanced methodology to support AESA in this challenge. However, where are we at AESA ready to implement the models that he has just outlined? As we said, 4 of our top managers entered an Operation Research postgraduate program, but at AESA, we are more than 350 persons, mostly aeronautical engineers, with little OR background. And as the proverb says, a prudent man foresees the difficulties ahead and prepares for them. The simpleton goes blindly and suffers the consequences. Thus, to overcome this important cultural challenge, the RIMAS project included several periodic training sessions for AESA engineers in OR and analytics to update our knowledge, present project advances, and capture functional requirements. In addition, we developed the RIMAS system, an architecture implemented in R, the popular advanced analytic programming language, that facilitates the implementation of our methodology, supporting all its phases, including the data load, the performance of various exploratory analyses, including correlation analysis, the undertaking of analysis of effects, the implementation of various forecasting models, and the assessment of outcomes, and the screening of occurrence through risk map and their conversion to risk matrices, and finally, the allocation of resources. all of them made in a user-friendly and functional manner, designed to guide the work of our engineers to the point that it has become a routine tool in AESA's operation. In the next 3 slides, I shall show you some screenshots from our system, RIMAS. This first one shows one of the screens used when performing exploratory analysis, presenting the annual evolution of occurrences per severity over 7 years. The second one presents a pre-filtered correlation analysis, showing the correlations of 8 occurrence types. Lighter blueness indicates a smaller correlation. For example, hard landing is highly correlated with flight management. And the last one of the screenshots shows a view of one of the forecasting modules included in RIMAS, referring to monthly forecasting of number of operations, a key ingredient in forecasting occurrences and, consequently, in estimating expected losses and optimizing resource allocation as sketched above. With such training and system, we felt ready to apply the methodology which we have done with great success, as reflected here by AESA's Director of Safety Analysis and 2 of our stakeholders, an airline pilot and an aviation service provider safety manager. Next video.
RIMAS is a major change in the way that we as a state identify and prioritize our aviation safety issues. Our main factor is safety. Now we can have a forecast about what is going to happen next year depending on the actions we are taking. It's the possibility to develop predictions with the model.
In ENAIRE, we share the path taken by the Spanish authority, by AESA, incorporating some new methodologies in the risk management process.
For example, if we have to focus in the bird strike problems, or we have to focus in the TCAS problems, or we have to focus in the maintenance problems, or we have to focus in the VFR flights or IFR flights.
As illustrated in this video clip, different stakeholders are involved in aviation safety. And as an example of the impact of RIMAS, we may take a look at some results for the operations in 2017 for the 3 most important outcomes: fatalities, crashed aircrafts, and accidents. In red, we showed the 95% predictive intervals for 2017 had we not implemented the policies suggested by RIMAS based on data until 2016. In the blue line, we can see the same year, but taking into account RIMAS recommendations. We also mark the actual observation for 2017, which appears very unlikely had we not implemented RIMAS, but quite likely because of having implemented it. As we say in our industry, safety does not happen by accident. And it is also relevant to present the forecast of equivalent safety cost for 2017. Had we not implemented the RIMAS policy, whose 95% predictive interval was between 900 and 1,650 million euros, versus the actual cost for such year after implementing the RIMAS policy, which was near 800 million euros. An important reduction indeed. Moreover, the screenings that we undertake through RIMAS allow us to identify issues that require further risk management, studies, and, if required, additional measures from the authority and or the rest of the stakeholders at the aviation system. The 2 types of occurrences presented in this slide, loss of control in flight and flight management, this last one related to the complying with onboard standards operational procedures, for instance, are being appointed by RIMAS among those with more expected loss. As an example of the measures that AESA could implement is the emission of safety recommendations, like the one recently issued in relation with drones through educational videos and leaflets. Our achievements have deserved us presence in major national media and in major scientific journals in the area of reliability and safety, in major aviation safety events with the SMICG, AESA, or ICAO, and last but not least, in OR and analytics events like this one. We are also proud to have been asked about details for RIMAS by several organizations which suggest transportability of our scheme, in part because of our RIMAS system. These include other national aviation authorities like INAC and CASA, the Italian and Australian civil aviation authorities respectively. And it is easy to understand that the problems we faced as authorities are very similar, and for this reason, RIMAS could fit almost completely to their risk management requirements. And we also have shared our methodology with other stakeholders, like airlines, for instance, FedEx Express, or air navigation service providers like ENAIRA. Both of them in a process of include a predictive approach to risk management in their safety management systems. Finally, aviation is not the only domain where the organizations have to identify hazards, determine the risk, and allocate resources in order to mitigate and control them in the most efficient way. For this reason, other organizations interested in operational risk management at large, like Petronor, BBVA, or Red Electrica, have also contacted us in the past and could implement it an accepted methodology based on RIMAS structure and models. And of course, RIMAS has been used in courses in decision analysis, risk analysis, and forecasting and aviation safety. Before concluding, let us recap the transformational nature of OR and analytics at AESA, which put us on the way of becoming an analytics-driven organization. For this, we shall compare AESA before and after the implementation of RIMAS. Indeed, through the journey announced by Veronica, our approach to aviation safety has evolved from being reactive to predictive, from basing it on risk matrices to being based on advanced risk analytics, from using data as frequencies to using them as basis for advanced forecasting models, from occurrence being hard to compare to allowing their transparent comparison, from intuitive risk assessment to promoting one based on decision sciences, and from decision-making based on eminency to an evidence-based one, from ad hoc, disconnected Excel-based implementation to a fully coherent architecture in R, from performing like other aviation authorities to leading the analytics transformation. This is well reflected in the views of our CEO, Isabel Maestre, in the next video.
La fortaleza de una cadena es la de su eslabón más débil. Con RIMAS podemos actuar sobre el eslabón más débil. Esa diferenciación nos permite mejorar mucho más rápido en seguridad aérea.
Let me finish with some considerations about this open door. As we all know, aviation is very sophisticated from a technological point of view. However, little use of operation research and analytics has been made in aviation safety beyond risk matrices. To our knowledge, this is the first time that these disciplines have been used in a preventive approach to state safety oversight in civil aviation. Moreover, as an important outcome, AESA is on its way to becoming an analytics-enabled organization, as reflected by many operation research-based smaller projects triggered by RIMAS, and our continuous improvement of the RIMAS system and methodology. Over these 3 years, RIMAS has had a positive impact on cost reduction. For example, as Frank mentioned before, in 2017, the actual equivalent safety costs were of about 800 million euros, whereas had we not implemented RIMAS, we would have very likely incurred in step costs between 100 and 850 million euros. Yet, RIMAS is having as well interesting positive environmental impacts derived from smaller safety occurrence-induced delays. Such delays entail relevant fuel consumption and CO2 emissions. As you can see on the screen, for example, in the case of a Jumbo, 1 minute taxi means 147 pounds of fuel and 465 pounds of CO2. Finally, and most importantly, this is mainly about avoiding accidents. This is mainly about saving lives, and this has no price. Thank you so much for your attention, and have a safe flight.